Welcome to this first video lecture, which covers the first half of Chapter 1. I am your instructor, Norman Sedgley, and this is the first video of our summer course. There's some information here that might be useful to you. My office is in Sellinger Hall 400, though I'm not there very often in the summer. But you can still reach me at extension 2848. That's my office phone, but it's linked to my email so that there's an alert if anybody tries to call me and I'm not in my office. Or you can email me directly at nsedgley@loyola.edu. All of this information is also available in the course syllabus. Here is your textbook, Anderson, Sweeney, and Williams, Essentials of Modern Business Statistics, 6th edition, with Microsoft Excel. We will be conducting most of our statistical analysis with Excel, and that will be an important skill to learn how to do the statistics that we cover using a modern software package. Here are some examples of statistics. Trump's approval rating is 36%. You can imagine that this statistic is quite important to Trump and to Trump's political rivals. Here's another statistic, the national unemployment rate, which is now at about 4.8%. This is a statistic that's very interesting to economists, to policymakers. For example, at the Fed, they look at the unemployment rate as a key indicator of the business cycle, and it's one of the most important variables that economists look at the Fed when they're determining whether or not they should raise or lower interest rates. The average time to close a trouble ticket at a tech support center is 23 minutes. That's another example of a statistic. This would be important to a business person at a company who had tech support as a major component of customer service, for example. This could be an important metric of how well customer service is working. Here's another statistic. The number of people who visit a web page per minute is 48. That's an important statistic, perhaps if you are in marketing. If you have a web page that receives more visits, then the owner of that web page is able to charge a higher price for advertising on that web page. So statistics are varied. We're bombarded by them literally all day, both in the media, the newspaper, on the internet, on television, and even in the workplace. But statistics is really more than just numerical facts like the averages and percents that we saw on the previous page. There are lots of different numerical statistics, including medians and index numbers and some other statistics that we haven't seen yet. We'll cover those later. But statistics more generally is a discipline that refers to the art and science of collecting, analyzing, presenting, and interpreting data. And so each one of these steps is very important in statistics, but this class is mostly going to focus on the analyzing, presenting, and interpreting the data. Most of the data that you're going to use, I've already collected and I've already shaped the data to make sure that the data is in a format that's clean and tidy and ready for analysis. But you should know that so-called ETL, that is extraction, transformation, and loading of data, is a very time-consuming task in most data analytics projects. And so we're not going to see a lot of that ETL type work in this class because the focus is going to be on the analysis and the actual statistic inferences. But all the data that you look at has been collected by somebody, in some cases me, and it takes quite a bit of work often to get data into shape so that it's ready for statistical analysis. I think that you should be aware of that. Data and data sets. So data are the facts and figures that are collected and analyzed, but if we take all the data together, we refer to that as the data set. I'm going to show you a data set here that comes from Kaggle, which is a data science competition website, and they had a competition to forecast department sales for Walmart stores. They collected data on 40 some odd Walmart stores at different regions all across the country. There are about 79 or so different departments within a Walmart store, and they collected that data over several years looking at weekly sales figures. We're going to take a look at that data set from a couple of different angles in our discussion of data and the components of data sets. But here's a data set that we call a cross-sectional data set. In other words, all the observations occur at one point in time. You can see that I extracted data here using a program called Python. I put this together. And I extracted data on just one date, on 2/5/2010. So in February of 2010. And I looked at all of the different departments that are in one store, the store that was coded as store number 1. So because I've got a fixed date and a fixed store, a lot of these variables don't vary very much. And they're not very interesting if they don't vary. But the real piece of data that we're interested in here is weekly sales. That was the goal of the data science competition, was to forecast weekly sales. So let me say a couple of other things about the data set in terms of definitions, which we'll see more of on the next page. This whole grid, this whole matrix really is the data set. This data set is in what we call long format because the variables show up in the columns. So the variables are the different aspects of whatever it is that we're studying, that we're interested in. Here we're interested in studying stores and the departments within store number 1 at Walmart. And the different characteristics that we're interested in are all of these different variables, and in particular here, weekly sales. So weekly sales is what we call a variable. The different departments within store 1 are what we call the elements. That's what your textbook calls the elements. And if we look at all of the different values of the variables for one particular element, then we're talking about an entire row that is in the data set. And that's called an observation. So we'll see each of these definitions on the next page. Again, here we go. Very quickly, elements are the entities on which the data is collected. In the previous example, that was departments within Walmart store number 1. A variable is a characteristic of interest of the elements. Those showed up in the columns, for example, weekly sales. The set of measurements obtained for a particular element is called an observation, so the observations show up in the row of the table. A data set with n elements contains n observations. That, I suppose, is fairly obvious. And then the total number of data values in a complete data set will be equal to the number of elements multiplied by the number of variables. In other words, the number of cells in the table is equal to the row dimension times the column dimension. That, too, I think is fairly obvious. We're going to talk also about scales of measure. There are different types of variables. When we talk about scales of measure, we talk about nominal and ordinal type data. These two types of data together are called categorical data. And then there's interval and ratio scale data. And this data, these two types of data together, we call quantitative data. We don't use the term numerical data because both nominal and ordinal data, categorical data if you will, as well as quantitative data can be coded numerically. The scale really determines the amount of information contained in the data, and it determines the types of analyses you can do with the data and the types of graphs or tables that are appropriate for that type of data. So it's important to understand the scales of measurement. Nominal data first. Nominal data is data that represent unordered categories or labels. So if you think of labels where the ordering of the labels doesn't matter, you have a nominal variable, an example of a categorical variable. Some examples might be race or gender, the department that you work in within your organization, or perhaps the state of residence that you live in. These are all examples because you can think of them as labels, but the ordering of the labels doesn't matter. Take gender, for example. If I'm coding a data set and I have males and females, I could code males as 0, and I could let a variable take on the value of 1 if the individual is a female. That would be a way of identifying females in the data set. But I would have exactly the same information if I coded males as 1 and females as 0, since there's no particular order to being a male or a female. The same is true for all of these other variables, making them examples of nominal variables. So it's really a non-numeric label or a numeric code where a numeric code may be used. Oftentimes we will want to take categorical variables and we will want to code them. as numerical variables before we use them in a data set. The other type of variable which is categorical is called ordinal, and it has all of the properties that nominal data had, except that the order or the rank of the data is meaningful. And you can think of examples of this, such as the rank of sports teams. It means something to be in first place as opposed to being in third place. Another example would be bond ratings. Bond ratings typically start out at AAA, then they move to AA+, etc., all the way down to junk bonds or a rating of F. Clearly, it's better to have a bond, and it's easier to borrow money if you have a bond that's rated AAA as opposed to a bond that's rated as a junk bond. So the order actually matters, and the variable is also categorical, or these are different labels, first, second, third for sports teams, or AAA, AAA+, etc. for bond ratings. Again, these are non-numeric labels, but numeric codes may be used, and oftentimes we're going to want to code these things numerically to use them in statistical models. Scales of measurement. Nominal and ordinal data together, I've already mentioned, are called categorical data. One thing I should mention is that if you have categorical data and the number of categories is greater than 2, then it's convenient to create actually n-1 separate numerical variables. We'll see explicit examples of this when we cover regression analysis in Module 3. But as a brief example, suppose we are talking about bond ratings. If we have a number of different bond ratings, say 6 different bond ratings, then we might want to start with AAA and create a variable which is equal to 1 if the company has a AAA rating and 0 otherwise. Then we would move to another categorical variable. This variable would be, say, AA+. And we would code that as 1 if the company had a AA+ rating and 0 otherwise, etc., coding that type of a variable for each and every one of the categories until we get down to the next to the last category. That next to the last category, say an F rating in our bond rating example, would be our baseline category, and we would be comparing all of our other categories to that baseline category. Categorical data can be numeric, and if it is numeric, it's what we call a discrete variable, because it can only take on particular values but not values within an interval. For example, if you code individuals as 0 if they're male and 1 if they're female, it doesn't make a lot of sense to code them as a 2.5 or a 1.3. It's either a 0 or it's a 1. So that would be an example of a discrete variable. Scales of measurement interval data. This is an example of quantitative data. Interval data are data which will come to us as numbers, so they will be numeric. And in interval data, we'll have all the properties of ordinal data, but the interval between the observations will be expressed in a fixed unit of measure, and therefore will be have an interpretation. So an example might be IQ tests. If we take IQ tests and one individual scores a 130 and another individual scores a 100, then it's meaningful to say that the first individual scored 30 points higher than the second individual. So that's an interval scale. Interval data, as I mentioned, are always numeric. Ratio scale data. Ratio scale data is data that have all the properties of interval data, and the ratio of the two values is meaningful. Examples include distance, height, weight, and time. For example, consider age. That would be another example of ratio scale data. If I have one individual who is 20 years old and another individual who is 10 years old, it is certainly data which is interval scale, because we can say that the first individual is 10 years older than the second individual. It's also ratio scale data because 20 divided by 10 is 2, so the first individual is twice as old as the second individual, and that ratio has meaning as well. Ratio scale data will always come to us as numeric data as well. Together we call interval and ratio scale data quantitative data. In general, quantitative data has more information than categorical data, and generally there are more statistical techniques that we can apply to the analysis of quantitative data than to the analysis of categorical data. So here's a schematic of what we have been talking about. Data in general can either be categorical or it can be quantitative. Starting at the right here, quantitative data is always numeric. And there are two cases, interval scale data and ratio scale data, where ratio scale data has all the properties of interval scale data, but the ratio of the values has meaning as well. Categorical data can be coded either as numeric or non-numeric, in other words, as labels. Typically, we will want to code categorical variables as numeric data before doing statistical analysis or including them in statistical models. This data can either be nominal, in which case the order doesn't matter, they're just simply labels such as gender or race, or they can be ordinal, like the rankings of a sports team, or bond ratings, in which case this variable has all the properties of nominal data, but the order of the data actually matters as well. And that's true whether we've coded the categorical variable as numeric or non-numeric. Cross-sectional data are data that are collected at approximately the same point in time, and we saw examples of cross-sectional data when we looked at our Walmart data set. We had one store at one point in time, and our observational unit was the departments within that store. That was an example of a cross-sectional data set. Time series data are data that are collected over several periods of time, typically on just one element. For example, we might look at one store, or we might look at one department within one store and track those sales over several years. For example, we might look at Walmart weekly sales for Store 1, Department 1 for the period 2/5/2010 out to October 26 of 2012. Graph of time series analysis or time series data will often help us understand what has happened in the past, identify trends over time, and project future levels for time series. Time series models, though, are a very advanced topic, and we will only have time to take a brief look at time series forecasting at the end of the class. Here's an example, though, of time series data from the Walmart data set. Again, I'm looking at Store 1, but now I'm also fixing the department at Department 1. So I'm only looking at Department 1, but you can see that now the data is changing. There are actually more observations in this in the data set. You're only seeing about the first 11 or so observations here, but you can see that now the variables are changing. Over here we have weekly sales, which changes each week for this department within this store. The consumer price index is varying from week to week. The temperature, the average temperature, is varying from week to week, as is the unemployment rate, although I would assume that that's a monthly variable, so you can see it change each month. You've got fuel prices varying from week to week, and then there's this categorical variable, is holiday, which is true if a federally recognized holiday falls on that day, and false otherwise. So you can see that there's a federally recognized holiday that falls in the week of 2/12/2010. So there's an example of quantitative data, and is holiday is an example of categorical data. Here's a graph of the time series, and you can see the patterns in the graph. These are useful to identify. For example, we can see that there tends to be a spike in weekly sales for this department that seem to run in about 4 different spikes from, say, here to here. It's fairly periodic and repeats, which might suggest that we can forecast these different spikes in sales using statistical models. We'll talk more about that later.